Let's first study about simple microscope. Simple microscope is a convex lens of short focal length held close to the eye. Now let's find how the magnification of a simple microscope is measured. An object AB is kept between the optical center and the focus of a simple convex lens. Now first let's trace the image, how the image of this object AB is formed. So for that, we take two rays which is emerging from point A. First ray, which is parallel to the principal axis, after refraction through the lens, passes through the focus. Second ray, passing through the optical center, goes undeviated. Now as you can see that both the refracted rays are diverging away from each other. So when these two refracted rays are extended behind, then at point A dash, both the rays coincide and we obtain an image A dash B dash, which is virtual and enlarged. Say the object AB is kept at a distance x. The image which is formed, A dash B dash, is formed at a distance d. D is the least distance of distinct vision. Now, as normal eye can see an object clearly at the least distance of distinct vision, which is 25 centimeter. The magnifying power of a simple microscope is given by this formula, that is angle subtended by the image at the least distance of distinct vision divided by angle subtended by the object at the least distance of distinct vision. Now, since the image is formed at least distance of distinct vision, the angle subtended by the image on an eyepiece or on an eye of an observer, which we consider it as almost the same, say we call this angle as beta, which is the numerator of this formula. Similarly, in order to obtain the angle subtended by the object, we drop a perpendicular from A onto A dash B dash, which meets A dash B dash at A double dash. Now A double dash B dash and AB are of almost same length. Now the angle subtended by A double dash B dash at O is represented as alpha, and this is the angle subtended by the object at least distance of distinct vision. Hence, according to the formula, magnifying power m is beta upon alpha. Now since beta and alpha are small angles, so we consider beta almost equals to tan beta and alpha almost equals to tan alpha. Now tan beta from the figure can be written as AB upon OB and tan alpha as A double dash B dash upon OB dash. Now A double dash B dash and AB are same. Therefore, we can write A double dash B dash upon OB dash as AB upon OB dash. OB dash upon OB equals to minus d upon minus x. As you can see, OB dash is the distance of the image, which according to the sign convention would be minus d, and OB is the distance of the object, which again according to the sign convention would be minus x. Therefore, m will be equal to d upon x. Now let f be the focal length of the lens. V will be equal to minus d, and using lens formula, which is 1 upon V minus 1 upon U equals to 1 upon F, we can write 1 upon minus d minus 1 upon minus x equals to 1 upon F, or 1 upon x equals to 1 upon d plus 1 upon F. On multiplying d, on left hand side as well as on right hand side, we obtain d upon x equals to 1 plus d upon f. Hence, the magnifying power formula for a simple microscope where the image is obtained at least distance of distinct vision will be m equals to 1 plus d by f. Now let's study about compound microscope and how magnification happens in it. The very first thing which we are going to do over here is to derive the formula of the magnifying power when image is formed at least distance of distinct vision. Compound microscope consists of two convex lenses. Lens which is closer to an object is called an objective piece, and the one which is closer to an eye is called an eyepiece. Image of an object is obtained at least distance of distinct vision. The final image of an object is obtained at least distance of distinct vision. Object AB is kept very close to the focus of an objective lens, as you can see over here. First, we will trace the image which is formed by an objective of an object AB. For that, we'll take first ray, which is parallel to the principal axis, after refraction through the lens passes through the focus. Second ray passes through the optical center, and both rays meet at point A dash, where A dash B dash is the first image obtained. This image A dash B dash which is obtained between the optical center of an eyepiece and the focus of an eyepiece. Now eyepiece enlarges this image A dash B dash further. Now for eyepiece, A dash B dash is an object, and in order to obtain the final image of A dash B dash, we take one ray which is passing through the optical center, the other ray which is parallel to the principal axis, after refraction passes to the second focus. Now when both these refracted rays are extended back, they meet at point A double dash. A double dash B double dash is the final image which is obtained. A double dash B double dash, the image which is obtained at a distance d, which is the least distance of distinct vision. AB is kept at a distance UO. A dash B dash is obtained at a distance V0 from objective lens. A dash B dash, which is the first image or an object for an eyepiece, is at a distance UE from an eyepiece. Magnifying power is given by angle subtended at the eye by image at least distance of distinct vision divided by angle subtended at eye by object at least distance of distinct vision. The angle subtended by image on eye is given by angle beta, and the angle subtended at eye by an object is obtained by drawing a triangle of base capital D, which is the least distance of distinct vision, and perpendicular of height h, which is equal to the size of an object. The angle which the object of height h subtends at a distance t is the alpha angle, which is the denominator of the magnifying power formula. M equals to beta upon alpha. Since beta and alpha are small angles, therefore we can write beta as tan beta and alpha as tan alpha. Tan beta can also be written as h dash upon ue. As you can see from the triangle a dash b dash e, a dash b dash would be the perpendicular and eb dash will be equal to ue. Similarly, tan alpha can be written as h upon capital D from this triangle. On simplification, we can write m as h dash upon h into d upon ue. H dash upon h can also be written as MO, which is the linear magnification formula of an objective lens, that is, the size of an image to the size of an object. And d upon ue can be written as ME, which again is the linear magnification formula for an eyepiece, that is, the distance of image, which is d, to the distance of an object, which is ue. Similarly, we can also write MO as V0 upon minus U0. Since magnification formula of an objective lens can also be written as distance of image of an since magnification formula of an objective lens can also be written as distance of image to that of a distance of object. Here, if you see in this figure, eyepiece is acting as a simple microscope where the object is kept between its optical center and focus, and we are obtaining a virtual image at the back. Hence, we can also write ME as 1 plus D upon FE, which is the formula of magnification for a simple microscope. Therefore, we can write M as minus V0 upon U0 into 1 plus D upon FE. Now, as a special case, an object AB is kept very, very close to the focus of an objective lens. Hence, we can write U0 as almost equals to F0, which is the focal length of an objective lens. And the image A dash B dash, which is formed from an objective lens, is formed very close to an eyepiece. So for all practical reasons, we can also take V0 as almost equals to the length of the microscope. So on replacing U0 with FO and V0 with L, the magnifying power formula can also be written as minus L upon FO 1 plus D upon FE for the image which is formed at least distance of distinct vision. Now, let's derive the formula of magnifying power for compound microscope when final image is formed at infinity. AB is an object which is kept very close to the focus of an objective lens. First, we will trace the image of an object AB formed by the objective lens. For that, we'll take first ray parallel to the principal axis, which after refraction passes through the focus of an objective lens, another ray passing through the optical center, and both the refracted rays meet at a point which lies exactly beneath the focus of an eyepiece. Hence, we obtain the first image A dash B dash from an objective lens at the focal length of an eyepiece. Now, since A dash B dash is an object for an eyepiece, therefore, the final image is obtained at infinity. We take a ray which is passing through the optical center of an eyepiece, which goes straight without any deviation. Another ray parallel to the principal axis passes through the focus of an eyepiece, and both the refracted rays are parallel. So when we extend these rays back, both rays are going to meet at infinity. Hence, we say that the final image is obtained at infinity. U0 is the distance of an object from an objective piece. V0 is the distance of the image formed by an objective. UE is the distance of A dash B dash from an eyepiece, and the magnification formula MO we can write as V naught upon minus U naught, which is L upon minus FO, since stop. The linear magnification formula of an objective lens can be written as V naught upon minus U naught, that is the distance of an image from the lens and the distance of an object from the lens. Now, since object is kept very close to the focus of an objective lens, hence for all practical reasons we can consider U naught almost equals to FO, and image A dash B dash is formed very close to an eyepiece. So again, for all practical reasons, we can consider the length of the microscope equivalent to that of a VO. So we can write V naught upon U naught as L upon FO. Linear magnification of an eyepiece can be written as D upon FE, which we have already obtained while deriving the formula of magnifying power for a simple microscope. Hence, the magnification or the magnifying power of the compound microscope for normal vision we can write as MO into ME, which is minus L upon FO into D upon FE. Although the credit of discovering the compound microscope went to Zacharias, but the credit of first telescope didn't went to Hans Lippershey. Adding the confusion, yet another Dutchman, Jacob Metzius, applied for a patent for a telescope a few weeks after the Lippershey. The government of the Netherlands turned down both applications because of the counterclaims. Let's study about the astronomical telescope. First, we'll derive the magnifying power of the astronomical telescope when final image is formed at least distance of distinct vision. Since the object is located far away, hence the rays coming from the objects would be parallel, and the first image which objective lens makes is at its focal plane. A dash B dash is the image which is obtained by an objective lens, and it is obtained between the optical center and the focus of an eyepiece. This image A dash B dash acts as an object for an eyepiece. So, in order to obtain the image formed by an eyepiece, we take one ray which is passing through the optical center, goes straight without any deviation. Another ray, parallel to the principal axis, passes through the focus. When both these refracted rays are extended back, we obtain the image A double dash B double dash, which is the final image, and it is obtained at a distance D from the eyepiece. Distance of A dash B dash from eyepiece is UE. Distance of A dash B dash from objective is V naught and also F naught, since V naught and F naught are same over here. Magnifying power of the telescope is given by angle subtended by image on an eye of an observer, that is this angle beta, divided by the angle subtended by object on an eye of an observer, that is this angle alpha. Now, since the size of the telescope is very small as compared to the distance of an object from it, hence the angle subtended by object on objective lens or on eyepiece is same. Therefore, over here, for the sake of simplicity, we are considering the angle alpha as the angle which is subtended by the object on an eye of an observer, over here. Now, since these two angles are vertically opposite to each other, we can consider this angle also as alpha. Magnifying power m, which is beta upon alpha, can be written as tan beta upon tan alpha, since beta and alpha are very small angles. Tan beta we can also write as a dash b dash upon b dash e from the triangle a dash b dash e. And tan alpha we can write as a dash b dash upon ob dash from triangle a dash b dash o. A dash b dash cancels and we get m equals to ob dash upon b dash e. Now since OB dash is FO and B dash E is UE, hence we write magnifying power M as minus FO upon UE along with sign convention. For an eyepiece, U equals to minus UE and V equals to minus D. And by using lens formula, we can write 1 upon Fe equals to minus 1 upon D minus of minus 1 upon UE. Hence we obtain 1 upon UE equals to 1 upon Fe in bracket 1 plus Fe by D, and the magnifying formula becomes equals to minus Fo upon Fe in bracket 1 plus Fe by D. Now, let's derive the formula for the magnifying power when final image is formed at infinity. Rays coming from the object will be parallel to each other, and the first image, that is the image which objective lens form, will be formed at its focal plane. Hence, A dash B dash is the image which is formed by an objective lens at its focus. A dash B dash is also formed on the focus of an eyepiece, because we need to obtain the final image at infinity. Hence, the adjustment of the telescope for normal vision is done in such a way so that A dash B dash is also formed at the focus of an eyepiece. In order to obtain the final image, we draw a ray which is passing through the optical center and goes undeviated. Another ray parallel to the principal axis passes through the focus of an eyepiece, and when both these refracted rays are extended back, they meet at infinity. UE is the distance of A dash B dash from an eyepiece. VO is the distance of A dash B dash from an objective, which also equals to FO. Same way, UE is also equals to FE, which is the focus of an eyepiece. Magnifying power is given by the formula angle subtended by image on an eye of an observer, that is this angle beta, and the angle subtended by object on an eye of an observer, that is this angle alpha. Now if this angle is alpha, its vertically opposite angle will also be alpha. Hence we can write magnifying power m equals to beta upon alpha. Beta we can write as tan beta and alpha we can write as tan alpha, since beta and alpha are very small angles. Tan beta can be written as A dash B dash upon B dash E from the triangle A dash B dash E, and tan alpha can be written as A dash B dash upon OB dash from the triangle A dash B dash O. A dash B dash cancels and we get m equals to OB dash upon B dash E. OB dash is plus FO and B dash E is minus FE. Therefore, we can write the magnifying power formula for normal vision as minus FO upon FE. It was in 1668 that Newton made his first reflecting telescope, having abandoned the attempt to improve refracting telescopes. He constructed his own tools to manufacture some of the parts. The reflecting telescope used parabolic mirrors rather than the lenses, and thus avoided the problem of color dispersion, that is the chromatic aberration, a phenomena that could prove very distracting to viewers of a magnified image. Before we study how the reflecting type telescope works, let's first understand what chromatic aberration is. When the white light passes through the objective lens of the refracting type telescope, it disperses because if we closely look at the cross section of the objective lens, each section acts as a prism in its own. Hence, when white light passes through the prism, it undergoes dispersion, and instead of obtaining one sharp image, we obtain band of colors. Now, let's understand the working of Cassegrain reflecting telescope. Cassegrain reflecting telescope consists of two mirrors. One is the objective mirror, which is a concave shaped, and another secondary mirror is a convex mirror, and it has an eyepiece, which is a convex lens. Incident rays from the distant objects are parallel and enters the Cassegrain reflecting telescope parallelly. When it strikes the objective mirror, it undergoes reflection. The reflected rays again undergoes reflection from the secondary mirror, which focuses the light onto an eyepiece. Hence, the final image is obtained at eyepiece. The final image formed at least distance of distinct vision and its magnifying power is given by the same formula which we have derived for the refracting type telescope, that is m equals to FO by FE 1 plus FE by D. This is for the least distance of distinct vision, and for normal vision we can write m equals to FO by FE, and we can write FO as R by 2. Hence we can also mention this formula m equals to R by 2 upon FE.